Section 20.4 Electronic Spectra of Complexes. Subsection B. The spectroscopic terms. This is the UV-Vis spectrum of hexaamminechromium 3. This is a D3 complex. There are 3 d electrons in this chromium 3. These 3 electrons each occupies one of the 3 T2G orbitals, dxy, dyz, dzx. And then in this electronic transition, we promote one of the 3 electrons from the T2G orbitals to one of the EG orbitals, dx squared minus y squared, or dz squared. And we explained why there are 2 different electronic transition energies in subsection A. This is because, well, we have 6 different ways of promoting one electron from here to here. And we can group this 6 options into 2 symmetry labels. And over here, this is the 4 T2G. This is 4 T1G. In this case, we have stronger electron-electron repulsion. For example, there are 3 different electronic transitions over here. 2 of them involve one electron occupies the dxy orbital. Another occupies dx squared minus y squared orbital. And these 2 orbitals are both in the xy plane. The 4 lobes of dxy and the 4 lobes of dx squared minus y squared are very close to each other. Therefore, there's a stronger repulsion in this case. The third way of the electronic transition here is after the transition, although you put the electron in the dz squared orbital, but then the other 2 orbitals are dyz and dxz. So dz squared and dyz are on the same plane. dz squared and dxz are also considered on the same plane. So there's still quite some electron-electron repulsion between dz squared and dxz, and between dz squared and dyz. So these 3 different options of electronic transition result in a higher electron-electron repulsion. So right here, you need more energy. And that's why you have a larger wave number here, 28,500. The 3 other ways include lower electron-electron repulsion. So that's why it's 21,500 here. The average is roughly delta O. Delta O is, I think, roughly 25K wave numbers. And the difference between this 28,500 and this 21,500 is 7,000 wave numbers that correspond to the difference in electron-electron repulsion due to the difference in their spatial distribution. Now I want you to look at this little peak here and this very large peak here. This is actually a very little peak. This is magnified already. And also, if you look at the vertical axis, it's the logarithm of the extinguishing coefficient. All right, so over here, why is this so small? And what does this mean? 2Eg. So you can see the spin multiplicity changes from 4 to 2. So over here, you have 3 unpaired electrons, each occupying a different orbital, and they have the same spin. That's Hund's rule. You have alpha, alpha, alpha. Now over here, still the 3 electrons, each occupies a different orbital, dxy, dyz, and dzx. Okay, 1 electron in 1 orbital. So don't worry about the electron pairing energy here. But this 2Eg has higher energy than this 4A2G. Why? In here, you have alpha, alpha, beta, or alpha, beta, alpha, or beta, alpha, alpha. All right? So now you flip one of the 3 alpha electrons to beta. All right? Electron flip is forbidden in electronic transition. So that's why this epsilon is so small. And 2, this 2Eg has higher energy than 4A2G because of the change in exchange energy. So what is exchange energy? Let's look at 2 different scenarios. In scenario A, you have 2 alpha electrons. In scenario B, you have 1 alpha and 1 beta. Suppose all other conditions are the same. The repulsion between 2 alpha electrons is smaller than the repulsion between 1 alpha and 1 beta. The reason is simple. In quantum mechanics, we learned that electrons are fermions. Their wave functions, the total wave function of multiple electrons, will have to be anti-symmetric. It's one of the quantum mechanical postulates. And that means if 2 electrons have the same spin, they cannot occupy the same spatial orbital. And that means, well, physically, they are farther away from each other on average. And that means lower repulsion on average between 2 electrons with the same spin than 2 electrons with different spins. So that's why this 2Eg has higher energy than this 4A2G. Over here, there's actually another peak here. It corresponds to this charge transfer motion of the electron. So in this case, either an electron moves from the transition metal to the ligand, or from the ligand to the transition metal. Either way, this charge transfer causes a significant change in the electric dipole moment in the complex. And whenever there is a significant change in electronic dipole moment, the absorption coefficient, this epsilon or extinction coefficient, is really large. Alright, so usually the epsilon of a charge transfer band is 100 times larger than this, and this is 100 times larger than this, I think, or maybe more. So this probably is 1,000 or 10,000 larger than a spin forbidden transition. So again, epsilon is the extinction coefficient or attenuation coefficient. It tells us how strongly a chemical absorbs a light at a given wavelength. So those are the wavelengths in nanometers. The wave numbers are the reciprocals of the wavelengths. And we explained why there are 2 different electronic transition energies when we promote electron from T2G to EG. And over here we explained this transition is forbidden. It's spin forbidden. That means you can't just arbitrarily change the spin of electron from alpha to beta or from beta to alpha. That's why the intensity of this transition is extremely low. So this is small enough, but this is already magnified. Okay. And then charge transfer. Epsilon, this extinction coefficient, is particularly large when the electric dipole moment changes significantly in a charge transfer process. So again, that explains the 4 peaks, the relative intensities, and also why this peak is a spin forbidden process, and thus has a very small epsilon. Oh, by the way, this number is roughly 15,000 wave numbers. That corresponds to the so-called exchange energy. Again, when you have 2 electrons with opposite spin, in this case, it has more repulsion energy than two electrons with the same spin. That's why these two spin multiplicity have different energy here. All right, so roughly 15,000 wave numbers. That's about, I think, 1.8 electron volts and 180 kilojoule per mole. So that's pretty significant.